Okay, to the question, how would you use the cross product to find the angle between two vectors? The definition, well, not the definition, but one property of the cross product is that the magnitude of the cross product is the product of the magnitudes of the two vectors and the sine of the angle between them. They're completely analogous in form to the fact that the dot product is the product of the magnitudes of the vectors multiplied by the cosine of the angle. Now, this differs, the cross product differs a little bit. You know that if it was the dot product, you would take the dot product and divide by the product of the two magnitudes, and that would be the cosine of the angle, so you'd be doing the inverse cosine. With the cross product, you can't just take the cross product and divide by the product of the two magnitudes. You have to have the magnitude of the two cross products. Okay, because in the first place, you couldn't take the inverse sine of a vector. If you didn't have magnitude of this cross product, you'd be trying to take the inverse sine of a vector, and you can't do that. Okay, so you need the magnitude there. But that's how you do it, and it follows directly from that property of the cross product, which I assume everybody is familiar with. Okay, if not, it's very easy to get familiar with it, and it's very much analogous to what we've been doing with the dot product. Okay, the next question is, if you have these 3 points, you want to get a vector, and you define the parallelogram, a parallelogram, I said the parallelogram, it's actually a parallelogram, by vectors, two of the vectors between these 3 points, okay? Two vectors between 3 points. So choosing this vector and this vector, I would get a parallelogram here. Okay, and let me emphasize that the way I've drawn these points has nothing to do with the actual angle between the points, has nothing to do with the relative distances between the points. I just slop down 3 points, call them 3, 5, 2, negative 4, 1, 2, 5, 5, 2, and I don't worry about anything else at this point because I don't want to have to do a lot of calculations. I just want a picture to represent the situation. Having drawn the picture of those 3 points, I'm going to draw a couple of vectors, and it doesn't have to be these two vectors. First place, vectors could go this way, or one of them could go in the opposite direction of one of these. Second place, I could use this vector and this vector to define a parallelogram, or this vector and this vector. There are at least 3 parallelograms that I could define in this way. But this is the one I choose. And a question arose in the class, would the area be the same if I chose a different parallelogram? Well, that's related to the A11, A12, A13, and so forth, and that's not relevant to the immediate calculation I'll do, but I'll come back and talk about that a little bit. Okay, so just based on the 3 points, I can get 2 vectors. Okay, now choosing this one, the vector from this point to this point, well, the I component will be negative 4 minus 3, which is negative 7. The J component will be 1 minus 5, which is negative 4. So the vector is 7I minus 4J. Vector here, 5 minus 3 is 2, so I have 2I. Well, 5 minus 5 is 0, so I don't have any J, and 2 minus 2 is 0, so I don't have any K. And I'm not sure I mentioned 2 minus 2 up here is 0. And of course, this tells you the fact that you have the same z-coordinate in all 3 is these vectors lie in a plane parallel to the xy plane. It's the plane z equals 2. You don't have to know that, but it's kind of worth observing because of the way things are going to work out. Okay, well, now I know that the parallelogram defined by these points goes here, and that the area of that parallelogram is the magnitude of this vector multiplied by the magnitude of this vector. Okay, so first place, the cross product of, well, we'll do V cross W. Cross product of V cross W is calculated here just using the distributive law. I just write the V vector cross the W vector, and then I times I is 0, so the negative 7I times 2I is going to give you 0. That just leaves you the negative 4J times 2I. Negative 4 times 2 is negative 8, and J times I Well, J vector is, if the y direction is there, x direction is here, z direction is here, J cross I is downward. It's negative k. So the negative 4j cross 2i is going to give me negative 8 times negative k, which is just 8k. And that's a vector perpendicular to this. Now, I didn't think to specify the area, and I think the question was asked. So the area is the magnitude of V cross W, and that's just 8. The magnitude of the vector AK is just 8. Okay, so whatever we get for the V cross W. Now, if we'd taken this vector and this vector to define our parallelogram, would it have had the same area? Well, we can test that. Okay, we could actually prove this by letting the coordinates of this point be A11, A12, A13, coordinates of this point A21, A22, A23, coordinates there A31, A32, A33. Now that should put you in mind of a matrix with first row A11, A12, A13, second row, third row. And maybe the area of that determinant might be something like, or the area of the parallelogram might be the determinant of that matrix, in which case it wouldn't matter, it might not matter which two vectors you use. So that question was raised. It was a very good question. So if we get the V vector by subtracting these coordinates from these coordinates, and a W vector by subtracting these coordinates from these coordinates, and write out what we would get in symbols. Let's see if what we get looks like something that would be the same had we chosen this vector and this vector, for example. So you might think about how to do that. It'd be an interesting thing to do and to work out.